Hello everyone, I'm delighted to present my research work cross-domain 3D hand pose estimation with dual modalities. My name is Lin Qiuxia. This work is collaborated with Yang Linling and Professor Yao. Through this video, we will first introduce you to the problem description of hand pose estimation. And then we will discuss the domain gap challenges in this problem. And we finally will present to you the solution to bridge the domain gap using synthetic data of multimodality and real-world RGB data. You can quickly get two main ideas from our work. First, learning the shared knowledge in multimodality could help reduce domain gap. Second, depth map can give RGB images task-relevant attention guidance for hand pose estimation. Let's move to the problem description. What is hand pose estimation? So given an RGB image, we can have a neural network to predict hand joint locations in 3D space or 2D space. The input could be also a depth map. But the success of deep learning-based methods have two limitations. One is the large amounts of training data. The other is the correct annotations. Clearly, the annotation for real-world RGB data is quite challenging and expensive, but it can be in the same distribution of real-world tested data. As for synthetic data, it can be easily generated with precise annotations and low cost. And also it can be multimodal data containing RGB, mask, and depth map. However, it suffers from the domain gap problem. In our work, we want to use synthetic data of multimodality and unlabeled real-world RGB data to perform model adaptation. But as we mentioned before, there's a domain gap. So how could we reduce the gap? We think that the gaps can come from the RGB images, which means that there are many task-irrelevant informations, and we find that depth map is a better modality that is less affected by the task-irrelevant information. And also, the multimodality could help the model more focus on the task-relevant information. So we want to explore the shared common visual cues across modality that are related to the underlying geometric or semantics. To this end, we propose a dual modality network. The pipeline of it consists of two stages. One is the pre-training on synthetic data of multimodality, and then we can have fine-tuning on real-world RGB data. In pre-training, we want to leverage the depth map to help the representation learning in RGB. To do so, we perform feature fusion. Specifically, we design an attention module, and we can use the attention from depth maps to get the learning in RGB. In this way, we will have three branches. Since synthetic data has label, then we can apply a attention-fused supervision on these three branches. Next, we want to explore the shared common visual cues across modalities. Here, we use feature alignment in these two modalities, which contains intramodal contrastive learning in RGB and the depth map respectively, and intermodal contrastive learning for RGB and attention-fused RGB. We compare our multimodal contrastive learning with other alignment methods, including L1 alignment and vanilla contrastive learning. The results show that the strong alignment between modalities that differ vitally may even bring negative effects, and our method could successfully explore the shared knowledge across modalities. After pre-training on synthetic data, we also have a fine-tuning stage to help adapt the model on the target domain. Since the target data is unlabeled, we would generate pseudo-labels and apply post-correction to filter out those of high confidence. Next, we design a self-distillation procedure based on our architecture. Specifically, for real-world data, we only have RGB, so we forward it into the network to have a depth map prediction. Then we use the depth map together with RGB as the input for the second pass. In this pass, we will have YF output, and we apply consistencies on YR and YF. In this way, the network is forced to be confident across multimodal predictions, and this process can help the model distill knowledge from itself. We evaluate our method on 4 datasets, and we can see that our method can outperform others both in 2D and 3D tasks. We provide some visualization before and after fine-tuning, and we can see that our method can get more complete predictions after fine-tuning. There are also some failure cases for our method, which are possible extensions for future work. In summary, we propose a dual modality network to address the cross-domain post-estimation problem in a semi-supervised setting. By leveraging the multiple data modalities, we explore multi-level alignment during pre-training, including multimodal contrastive learning and attention-fused supervision. During fine-tuning, we explore self-distillation and provide a unified fine-tuning strategy for real-world data. Thanks for listening.